Hello everyone and welcome. Today I will be teaching about asymptotic notations. But before I get started in teaching what asymptotic notations are, I just want to deep little dive into asymptotic analysis, the word which I highlighted in yellow. So asymptotic analysis is quite important, but it really doesn't require whole other video about it, so I just decided to combine it a little here because it's a short and sweet little concept. But basically what asymptotic analysis is, that it's basically a universal idea created in order to determine time complexity or efficiency of a program. So we all have, different computers, which means we have different hardwares, and it makes it a little difficult to determine time complexity of a program. But using this idea of asymptotic analysis, we can use this universal idea for everyone. So we can find the same time complexity or efficiency. It would be the same for each same program, no matter what computer or hardware you're using. So now that I've covered a little about asymptotic analysis, now we're going to dive into the asymptotic notation. So asymptotic notations are basically just mathematical tools or basically formulas to represent the efficiency of algorithms. Then let's go into these notations or formulas. Okay. So first up, we have theta notation. And this is how in computer science we write to represent the theta notation. Actually, all of these are like the symbols used to represent these notations, sorry. But the theta notation is what we call exact bound. And the reason why we call it the exact bound is if we look at this example. So in this example, we have n, and n can be 8, it can be 800, but n, here we have n to the power 3. Just right, this arrows means like to the power 3, right? And what theta notation basically means by that is that these numbers would be considered smaller, right? Because this is n to the power 3. This doesn't really have a power of anything, and this only has a power of 2. So these numbers would be considered smaller. But this number right here, not only is it powered to 3, like this one, but it's 3n to the power of 3. So this would be considered larger, and this would be considered smaller. So that's what we mean by exact bound. There are both smaller and larger numbers present. So that's why theta notation is known as exact bound. Whereas in big notation, I cannot say that word, notation, this would be an upper bound. And when we compare it to n to the power of 2 is always going to be greater than n, right? If our n is 10, then n to the power of 2, which is 10 times 10, 100, will always be greater than 10. So that's the reason why big O notation would be considered as an upper bound. Then lastly, we have omega notation. And this is basically a lower bound. And here we have an example of log n. So those of you who are not familiar with log n, let's say, we don't need to really go much in depth in it, but let's say for our n is 1,000, right? Then when I put in this formula, log 1,000, then this would output 3, right, in a calculator. And we can clearly see that contrast or that difference, that 1,000 is much higher than a 3. So that's why this is considered to be lower bound. Keep in mind, this is very rare, this usually almost is never seen, just because in terms of time complexity, this is like one of the best case scenarios you could see, right? That's the best. But in computer science, we always have to be prepared for the worst. So we should be prepared to see much upper and exact. So this is a very rare exception, but it can happen. So I think I might have made it clear, but I don't think I directly said it. Is that whenever we're saying, oh, exact bound, upper bound, lower bound, I want to emphasize that we're always comparing it to n. So in this case, n was 1,000 and 3 was much, much, much lower than our n. That's why we labeled it as lower bound. Whereas in big O notation, it was that n to the power of 2 was much higher than our n, right? So that's why it got classified as upper bound. And then same for Theta notation. But whenever we're comparing it, just know we're always comparing it to n, like with lower, upper, and exact. So yeah. Lastly, I just want to wrap up the video by saying some properties of our notations. So these two apply to all three notations which we learned today. So the first one is transitive, and transitive is basically A equals to B, and if B equals to C, so if these two are true, then we can already say that A equals to C. So if these two statements are true, then this must be true. So in this one, basically, what we said is Fn equals n, okay. Gn equals n to the power of 2, okay. Hn equals n to the power of 3. So do we see a little what's happening here? Like, it's just increasing the power, but okay. Then n, this is a big O notation, n to the power of 2. And if n to the power of 2 is O to the power of 3, right, we're going right, then n must be n to the power of 3. So basically, if Fn equals this, and this equals this, then these two have to be equal. So that's what transitive property is all about, and that's how we apply it into computer science with our notations. Then we have reflexive, and basically the rule of reflexive is that A equals to A. So, okay, A equals to A. So it's saying that X equals to YFN, and Y equals OFN, right? So they're same thing. Then Fn equals n to the power of 2. So this is basically our X. And O n to the power 2 equals Y. So same thing, these are the same, and they just equal that. So this would be case of reflexive. So there are more properties like such as symmetric, but symmetric would only apply to theta notation. But these two properties apply for all three of our notations, so that's why I covered them today. But I hope that you have had a good idea or learned a little about notations today, and enjoy.